Okay, so you can obviously use the same picture in this question when you work with it. So I'll just quickly transfer the picture over, and then we'll see which one we prefer this time. And again, it is possible to do it with either method. It's just that one preference may be better than the other. So here's my axes. This time it says I'm rotating it around this line, and this is the region again that we're working with. So that is going to be rotated around here. So what do you think? Shell method, disk method? Why shell method?
There's an empty space with this.
Maybe. One integral? Yeah, that would be the reason. That would be the you know, if I was to pick a reason, I would say because there's only one integral if we use the shell method. So if you, same picture, so it's going to be the same idea. When I put my shell, because it's parallel to what I'm rotating, that means this time when I set up the integral, it's going to be a shell method. It's parallel. And then I only have the one integral. If you go vertically, then you end up with that same issue, that you have two regions. So not that you can't do this with the disk method, I just think you'll find one integral is a little easier to work with. So for the shell method, it's 2 pi RH for the area of the shell. So the volume is going to be 2 pi, and we're going to go from, this time we're doing it with respect to y. So here's y equals 2 up to y equals 6. So that's what I'm going to be integrating it from 2 to 6. And let's see here. The radius function. The radius is this. If you picture it spinning parallel, this is my radius here. So the radius function is going to be 6 minus whatever the value of y is. And the height of the disk is this piece here. So the height, again, is going to be 6 minus 6 over y. One small correction to make here. I think I might have had my bounds wrong on the last integral. Let me just take a quick look here. Yeah, did I? Yeah, this one here should stop at 1, not 3, because that's where the integral would stop at x equals to 1. So my apologies, but that bound needed to be fixed. Okay, so any questions so far? Getting some strategies, getting the hang of it? Okay, so let's take a look at the next question. So at this point, again, we'll go with what we've already been doing. Just set it up, we won't solve it. The solid revolved by the region when it's revolved around the y-axis, and then we'll try it again around the x-axis. So it's a good way for you to compare what methods you'd be using on the same question. Okay, so the graph should be pretty easy for you. I'll give you a couple minutes and we'll catch up. Okay, so I'm going to get a picture going. I'll probably do one for each, but okay, so here's roughly what the parabola will look like. The line x equals 2 and y equals 0 is the x-axis. So the piece that we're looking at is this region in here. And it's going to want to take that region, revolve around the y-axis. Okay. So, well, it would be nice if I could, the way I've got this set up, it would be nice if I could use a dx. So what I'll do is I'll just take a look at, if I was to go on that journey using dx, what would my problem look like? Okay. Well, those look like shells to me because they're parallel. How hard is it going to be to do the shells? Well, again, it looks like there's only one integral. It's going to go from 0 to 2, and it's going to use this top one minus well actually it's because it's at 0 here, it's just the height, it's already given to me as 2x squared. So I'd say at this point I'm pretty convinced that I want to do the shell method on it. So let's come up with an integral. So for a shell, it's 2 pi, and we're going from 0 to 2 because we're doing it with respect to x. My radius function, if I'm rotating it around the y-axis, this is my radius here, which is whatever the value of x is at that particular position. So the radius function is x. And the height is this one here. That's my height, and I know it's 2x squared if you give me the value for x. So this is going to be 2x squared for my radius and height function. Okay, so if we just wanted to set this up, then maybe we'd do one more step here. So 2 pi from 0 to 2 up to x cubed. Okay, so we'll take a look at the x-axis revolution. So this time, same picture obviously. Might be better if I was to maybe zoom in a bit more on the area that I'm interested in. So it's the same figure going around the x-axis this time. So this time, if I think about it, we already talked in the first part, this is the nicest rectangle to deal with. So if I use the same type of rectangle, right, this is a disk method question, and it is a dx, which I've already got in my information that's given. So it's not so bad if I wanted to rotate this around. The volume this time is going to be, since we're using the disk, there's no hole, it's not a washer, so it'll be pi. We're going from 0 to 2, so from 0 to 2 of the radius squared. So the radius in this picture is up to 2x squared. So 2x squared all squared. So again, if I was to just leave the integral without evaluating it, if I go from 0 to 2, it'll be 4x to the 4 dx. Okay. Any other questions? I have a question for you. Obviously the pictures look different. The one on the right looks like it's got a bigger area. But instead of thinking about the area, see if you can picture what kind of shapes you think these are going to make. Right? Visualize it. What's it going to actually look like? Can you describe one of them to me?
Satellite.
Sure, go for it, Joy.
Like the satellite.
Yeah, this one's going to kind of look like a satellite dish or a bowl. Yeah, Tanya. Yeah, the second one's going to look like a cone or maybe like a trumpet kind of flared out once it's rotated around. So it's still important that you take the time to visualize it when we do those. Okay, so